Hello and welcome to today's video. Today we'll be looking at a problem, and the problem says that a 500-pound force is applied to a bracket as shown in the figure. The bracket is held in static equilibrium by a pin at A and a roller at B. So a pin at A means that the pin is having an X and a Y direction, and then the roller has only one direction. That's what they are trying to say. Only one force in one direction. So this one is at an angle. We are going to resolve it later. I'm saying that the bracket is made of a 1.5 inch by 1.5 inch squared and has a thickness of 0.5 inches. First, sketch the free body diagram of the bracket BCA. B. Determine the magnitude and direction of all external reactions acting on the bracket. C. If the modulus of elasticity of the pipe material is equal to 29 times 10 to the power 6, determine the change in length. D. Determine the normal and shear reaction on sections AA shown in the figure of the bracket. Then E. With the exception of the transverse shear, determine all stresses that might be acting on the surface of the section AA and represent each stress on a stress block. F. Combine the stresses into a combined stress and sketch the stress block. Then using Mohr circle, determine the principal stresses and principal planes and maximum in-plane shear stress. Basically sigma 1, sigma 2, and then tau max and sigma theta p. That's basically what they're asking you to find over here. So let's go through the question quickly, and then I hope by the end you'll be able to understand. Okay, basically the free body diagram is just the structure. So draw the structure, indicate the forces and then their distances from each point. So basically this is the structure of BCA. First of all, we indicate the force at the B. So it's a ruler, so it has one reaction which is R. So we name that reaction R. Then resolve the angle over in terms of theta. So cos 45 sin 45, we do that. And then A will also have an X and a Y direction to AX and AY. We do that and we get our AX and AY. Then we add our distances. We add our another force which is 500-pound force. We do that and then we get 500-pound force. Then we add our distances to it. We add our distances and then we get our E. Okay, we get our E. And this is our free body diagram. Now the next question is saying that we should determine the magnitude and direction of all external reactions acting on a bracket. So external reactions are basically R, AX, and AY. Those are the external reactions. So we'll do the normal. Basically, if you have a free body diagram, you sound force in the X direction, you sound force in the Y direction, then you take moment about one of the points. So basically, this is the free body diagram. First of all, we sound force in the X direction. We sound force in the X direction. We are saying that anything going to the right is positive. So R cos 45 is going to the right, so it becomes positive. Then AX is going to the left, so it becomes negative, and we leave it this way. Then in terms of summation of forces in the Y direction, we are going to say that R sin 45 is going up, so it becomes positive. Then 500 is coming down, so it becomes negative, and AY is going up, so it becomes positive. And then we get our sigma, our Y to be that. Now we want to take moment. If you take moment about R, we are going to be seeing AX and AY, but we don't want that. We want to eliminate AX and AY. So we take moment about A, and then we can find R easily, and then we can just put R into what these two formulas, and then we get our AY and AX. So first of all, we take moment about A clockwise, and this is what we get. So if you take it clockwise, R cos 45, perpendicular distance is what, 7 plus 8, which will give us 15 over here. Then it's going clockwise. Then R sin 45 is also going clockwise. Perpendicular distance is what, 15. 10 plus 5 is what, 15. Then minus 500 is going down, so anti-clockwise. So 500 times 5 is going to be equal to 0. We get R to be equal to this. If you find it, well, you get R to be 117.85. Then we put R into this equation and this equation, and then we get AX and AY to be 83.32 and 416.68 respectively. Okay. Now the next question is saying that we should what? If we should find a change in length of AC. So So you can see that AC is being stretched, being compressed by AY. If you look at it, it's being compressed by AY. So this is being compressed by AY. Then we are going to see that what is in compression, and then if you find the change in length. So our length, our original length of AC is going to be 7 plus 8. Our force applied is going to be AY. Then we know our E, our elasticity is 29 times 10 to the power 6. And then we know our area. They said the area, the pipe is 1.5 by 1.5, and it has a thickness of 0.5. The hole will be 0.5 by 0.5. So it will become 1.5 squared minus 0.5 squared to give us our area. Basically, our change in length is what? Force times our length over our E times A. So basically, you put your data down. When you put your data down, then you go on to solve for your what? Your change in length. Then that is just formula work. Then solve for change in length, and then that will be it for C. Now we move on to D. D says that determine the normal and shear reaction on a section AA. So a part as in section AA, as you can see from the free body diagram. Now if we draw that part very well, we are going to get this. So that part will be having AY and AX. AY will act like a compressive stress, and AX will act like a shear stress, basically. So we are going to, so this is how AY is going to act. And we know AY is what? The value is 416.68 pound force. Then what? That will give us our normal, that's in terms of our axial stress. Then our shear stress is going to be in terms of what? In terms of AX, which is 83.32, and a shear VA. So, and then there will be a moment. There will be a moment to MA. So there will be three reactions: a normal, a shear, and a moment, basically. So a normal reaction, we are going to get negative 416.68, showing that it's in compression. Then our shear is going to be 83.32, and then our normal is going to be 83 times 8. That's from the AE. So 83.32 times 8 is going to give us our moment, and then those are our reactions. Now the next question is saying that with the exception of the transverse shear stress, determine all other stresses that might be acting on the surface section A and represent each of the stress on the stress block, basically. So basically we are going to what? So this is basically the pipe. What I'm showing right now is the pipe. This one is the pipe. So it's just showing the area that we go. So first of all, we know that stress is equal to a force over area. The axial stress is going to be equal to the FA over what? The area. So our axial stress is going to be equal to what? FA over area. All we need to find is the area. We know the area already. We know FA. So we just find that the area is going to be what? The bigger minus the smaller to give us 2. We do that, and then we find our stress is negative. So our axial stress is going to be negative 208.34 psi, or pound per inch squared. So our stress goes basically, it's in the y direction. So it's going to be sigma y. So you're going to draw your EE, then you indicate your sigma y, showing in a compressive state. And this will be our stress block, basically. So after doing that, then we are going to go to our bending stress. Bending stress is basically what? Our moment times our neutral axis over what? Over our moment of inertia. So that's our bending stress. So basically put our data down. We know our moments from our reactions. Neutral axis is basically the height over 2. So that's 1.5 over 2, the height of the pipe, which is 1.5 over 2. And our moment of inertia, basically for rectangular objects or square objects, is going to be what? 1 over 12 BH cube. So we know our B and H is the same. That's why it's looking this way. But it's a hollow pipe. So which means that the bigger moment of inertia minus the smaller is going to give us our total moment of inertia. We do that, we substitute the values inside, and we get our bending stress to be equal to 1199.71 pound force per inch squared. Bending stress has the same similitude of stress block as the normal or axial stress. So it's not its intention, so it goes outward. So this will be our stress block for our bending stress. Then the last stress is going to be our shear stress. So for our shear stress, it's going to be that's our shear reaction over the area, basically. So just the shear reaction over the area. We know the shear reaction, we know the area. So we are going to find our shear stress to be 41.66 pound force per inch. And our stress block will be represented over here this way. And then we draw our arrows nicely. And then we get our stress block. So it's going to be our stress block. the direction over here and here shows that it's positive. If its direction is here and here, it's going to be negative. Okay, so basically that is it for the E. Now the F says that we should combine the stresses into a combined stress and sketch the combined stress block. So supposed to combine the stresses. So to combine the stresses, we are saying that what the combined stress sigma y is going to be negative 28.34 plus 119 because they are all in the y sense. So our sigma y, this is our normal stress, is going to be in terms of the compressive stress and the bending stress, giving us 991.37. Then our tau max is basically our tau xy is basically 41.66, and that is our combined stress is calculated. Then we draw our combined stress block. Basically replicate the same thing but just add everything together. So here it will be in tension, so we add it, and this is going to be our combined stress block basically. Okay, so that is it for the combined stress block. Now the gene says that using the Mohr circle, determine the principal stresses, the principal planes, and the maximum in-plane stress. So basically Mohr circle. When you are drawing Mohr circle, always we need three parameters. We need H, V, and C, where H is so we are plotting basically. So sigma is going to be sigma y comma tau xy, and V is going to be sigma x comma negative tau xy, and then C is basically the average of sigma x and sigma y comma 0. So if you have solved this already, you just input the values and then you plot. So the plotting is a sketch, okay, to give you a fair idea of how you are going to get the sigma 1 and sigma 2. So basically we plot our H, which is here, and then we also plot our C, which is here. We plot, so we just a rough sketch. Then we plot our vein, then we draw our line, we indicate our angles, then we draw our circle. So we draw our circle nicely, and this is our Mohr circle. We also indicate our tau max, which is also equal to our radius actually. Then we indicate our sigma 2, which is our minimum principal stress, and our sigma 1, which is our maximum principal stress, as you can see over here. So basically when we are done, we analyze it now. We analyze it using maybe coordinate geometry. So you can see that the radius over here, okay, is going to be it's like the slope, okay, the slope. So remember, if you're finding slope, is change in what? If you're finding the length of a slope, is change in x squared plus change in y squared, root of it. So root of change in x squared plus change in y squared is going to give us the slope, the length of the slope. That's from here to here. That's like the radius. So if you find the radius, you can see that there's a pattern, the center over here. Now the sigma is also what? Also on the circumference, right? You can see that from the center over here to this point is the radius, which means that center plus radius is going to give me sigma 1, and center minus radius is going to give me sigma 2 basically. From this graph, basically I can use this graph to find everything I need. Theta 2p, you just use Pythagoras theory. So the height of this one is what? 41.67. If you know the radius, you can find theta 2p easily. So let's go and do that analysis. So basically I'm saying that r is going to be what? Change in what? X squared plus change in y squared, root of it. That's the length of the slope, which is also equal to r in a sense. Now that's from the center. Then you know that what? Sigma 1 is what? The center value, which is what? 0.49 minus r. Sorry, so it's 0.495 minus r. So it's going to give you sigma 1 to be this. We're going to get 1.2 megapascal to be our sigma 1. Then for our sigma 2, we are going to get negative 1.75. Then for our theta 2p, when we indicate is that r is here and then the height is 4.16. So if you use sine theta is going to be opposite over what? Hypotenuse, and then we get our theta p to be negative 2.41. Negative in the sense that it's going clockwise to the positive x-axis. That's why it is negative. So it's clockwise, that's why it is negative. Thank you very much. This is the end of the question, and I believe that you understand. Thank you.